Welcome to Chemistry 211. This is lesson number 1. How this class works is I encourage you to go and pause this video and go find a piece of paper and a pen. I'd love for you to take notes with me. It's going to be really important in this class to develop a muscle memory. It's just like playing an instrument or a sport. The only way you're ever going to get good at organic chemistry is with practice. So if you're sitting in your bed, drinking tea, watching Netflix, watching this video at the same time, you are not going to learn chemistry very well. The best thing to do would be to go to a quiet place, focused place, an area that you dedicate for learning. Get out that piece of paper and a pen and write notes along with me. I'm going to go by nice and slow after this short little intro. I'm not going to just go through a PowerPoint slideshow. That's not what this class is. We are going to be writing. We are going to be doing things. So take notes along with me, and that's going to start developing that muscle memory. Now, if you've already taken notes and you're just watching this video as a review, don't forget you can always increase the playback speed down in the bottom right. So I encourage you, if you're just watching this video and not planning on taking notes with me, watch this video at double speed. Otherwise, this video is going to feel really slow because I'm going to write everything out, just like as if this were a real class. Okay, let's get started with organic chemistry. And the amazing thing about organic chemistry is you all are actually experts in organic chemistry already. When you woke up this morning, a molecule in your eye called transretinal underwent an organic chemistry reaction with visible light and turned into cisretinal. And that's actually how your eyes work. That's how your eyes recognize visible light. So you're an organic chemist. You're doing organic chemistry every single time you open your eyes. Then maybe before you watch this video, you took your doggy out for a walk. And when you did that, your body did another organic chemistry reaction. It converted glucose in a process called glycolysis into pyruvate, which is our body's energy source. Again, that's an organic chemistry reaction. You are a pro-organic chemist. And as you're sitting there right now thinking on your computer in this online class, neurotransmitters are being synthesized by your brain, by specialized cells. They're being released, and here's a few of them here. We've got dopamine, serotonin, acetylcholine. These are all organic compounds. They're all made using organic reactions, and your body needs these substances to survive. So you are an expert organic chemist. So the point of this class is, can we understand organic chemistry? And the answer is no, we cannot. In fact, nobody understands organic chemistry. All we have been able to do so far is create some models to help us understand some patterns, some trends. I am not at all promising you the answers to all of organic chemistry because frankly, they just don't exist. Instead, we're gonna try and understand the models that humans have created to try and understand this fascinating world. The first order of business is we need to be able to interpret structures like this. We see these what are called bond line structures a lot in movies and television. They're usually written on the chalkboard in some fantasy high school classroom on a TV sitcom. But what do these structures actually represent? What do these lines and symbols and letters mean? I mean, you probably recognize this as like oxygen and this is hydrogen and stuff, but like what's up with the bolded lines and the dash lines? What's up with the double lines and things like that? So we're going to talk about how to draw structures like this. You're going to become pros in interpreting structures like this. We'll talk about how these sort of names kind of come about. We want to also be able to talk using the English language to sort of, I can say a word and then a picture of a molecule will pop up in your mind. That'll be really important. And then we can start talking about what these molecules do, how they react, how we can build them. That's actually where we're going in this class. You are going to learn how to actually build any molecule you can imagine. It's amazing what we can do. Even though we don't really understand it. So what is organic chemistry? I see that my thing is kind of cut off here. Is there a way I can fix that, I wonder? Probably. There's probably a way that I can fix that. Okay, well, all it says here is what is organic chemistry? And maybe you recognize this device here, maybe you don't. Anyone know what that is? It's called a Leyden jar. And this Leyden jar represents that mankind has been trying for centuries, since modern science, to try and capture and tame the electron. So where did you see this Leyden jar before? It's here's Ben Franklin trying to capture lightning in a bottle. So there you can see the Leyden jar down here on the ground, and he's got his famous kite with the key on it. And the Leyden jar is an early version of a capacitor. It's designed to capture and store electricity. So the fascination with electrons has existed for a very long time. So organic chemistry is no different. Organic chemistry is just like this Leyden jar. It's trying to harness the power of the electron. When you look at organic chemistry at the kind of big picture level, it's actually defined almost exclusively by the movement of electrons. We don't really care about protons, we don't really care about neutrons, but electrons, which are represented by these little dots, are what are going to be causing reactions to occur. So if you just look at these two slides back to back, you can see that it's simply the movement of electrons that's causing the change in this organic molecule. Okay? So we want to try and understand, and we want to try and harness the power of the electron in this class. Now, what is the definition of organic chemistry? For a long period of time, organic chemistry was sort of defined as compounds that were found in living things. So it was believed that there was a sort of a sacred distinction between life and inanimate objects. And it was thought that there was a special quality bestowed on living things that inanimate objects could never have. Sort of at the time probably described as something like the breath of God. You know, this miraculous sort of supernatural or even religious at times belief that there was a distinction between the living and the dead. However, this sort of belief was not exactly able to withstand the test of science when Friedrich Wöhler performed this reaction. He combined ammonia, which is NH3, with cyanic acid, HOCN, and he found that he was able to obtain as a product urea. And so remember, this is a kind of reaction scheme. The starting materials are on the left and the products are on the right. And urea, for a long time, was believed to only be produced by animals and humans. So we kind of see this diagram here representing this division between the inorganic and the organic. And we can see that in an organic system, urea is formed. It's an important part of the urea cycle in our bodies, and you can learn about that in a physiology class or a biochemistry class. We're not going to talk about the urea cycle. However, urea can also be produced synthetically. So what is the actual distinction between organic chemistry and inorganic chemistry? There really is none. It was an old distinction, but has now been proven false. There's no difference between organic compounds and inorganic compounds. Literally anything that can be made by a human can now be made in the lab for most intents and purposes. There's no miracle distinction here. And but chemists still do like to separate organic chemistry from general chemistry. After all, you are in an organic chemistry class. So for the purposes of this class, we'll just define organic compounds as compounds that contain carbon and hydrogen. At first, a lot of chemists want to say, well, organic compounds are any compounds that just contain carbon. However, that had some issues because, like, for example, diamond, which is pure carbon, is clearly not organic in any way. It's like looks like a rock. So a better definition of organic compound, which is still just a hand-wavy definition, is carbon plus hydrogen in a molecule. So, for example, urea would be considered an organic compound because it contains carbon and hydrogen together. All right. So let's actually start with the content in this class. So now this is when you can start taking notes. And none of that stuff that I told you on the previous page, I'm ever going to test you on that. That's just for your curiosity, just to sort of align you with sort of the history of organic chemistry. And so what we're going to start this class off is by talking about structure. So we'll say this is chapter 1, and chapter 1 in your textbook, and this is called structure. Structure is referring to, of course, the connectivity between atoms that make up organic compounds. And section 1.1 is actually going to be a review from something you maybe remember from general chemistry, and that is Lewis structures. Lewis structures are very important in organic chemistry, so it's important that we review these. Lewis structures. Okay. Let's take a look at a organic molecule. Why don't we take a look at urea? So here's the Lewis structure of urea. We have carbon, double bond oxygen, nitrogen. There's 2 hydrogens attached to each nitrogen on either side. Okay, this is the Lewis structure for urea. And if we're going to be really accurate, of course, we would want to add in some lone pairs. Okay, so that's the valid Lewis structure of urea. Now, you probably remember back in general chemistry, there's a whole systematic way to draw these Lewis structures, but we're going to do a kind of shortcut here to help us draw Lewis structures more quickly. And the shortcut is called valence. So it turns out that certain atoms prefer a certain number of bonds as a general preference. And so it turns out that carbon prefers 4 bonds. And nitrogen prefers 3 bonds. And oxygen prefers 2 bonds. And hydrogen prefers 1 bond. And this sort of rule of bond number preferences is called valence. So carbon has a valence of 4, and nitrogen has a valence of 3. And so this can actually help us quickly draw Lewis structures, because if we have a bunch of atoms we need to connect, we just need to make sure that, okay, our carbon has 4 bonds coming out of it, and our oxygen has 2 bonds coming out of it, and our nitrogens should all have 3 bonds coming out of them, and the hydrogens should have 1 bond coming out of them. And it turns out the periodic table can help you predict the valence of other atoms as well. So let's take a look at the periodic table, and I'll post this on Canvas. Here's a beautiful periodic table that I use in my Chemistry 60 course. And you can see that most of the elements that are found in organic compounds are over here on the right. And so carbon has a valency of 4, nitrogen has a valency of 3, oxygen has a valency of 2, and all these halogens here actually have a valency of 1. And the noble gases have a valency of 0. And that makes sense because the noble gases don't like to make any bonds. So that's a quick trick to remember the valence of each atom. So, for example, phosphorus would have a valence of 3, just like nitrogen. And sulfur would have a valence of 2, just like oxygen, because they're in the same column. And then we didn't talk about it, but fluorine, chlorine, bromine, and iodine, which do commonly appear in organic compounds, they would have a valency of 1, just like hydrogen. So I'll go ahead and post this periodic table on Canvas. You can use any periodic table you want in this class. Okay. So when it comes to drawing Lewis structures, there are 2 things I want to mention. And the first thing is the Octet Rule, which you probably heard before. And the second thing is formal charge, which you probably also heard before. So let me just copy down my urea molecule down here so we can talk about these 2 things real quick. And by the way, in problem set 1, I will give you an opportunity to practice drawing some Lewis structures just for fun. Okay, so the first rule that we need to keep in mind is the Octet Rule. And the Octet Rule talks about how most elements prefer to have 8 electrons. Octet referring to 8, of course. To get to the number 8, here's what you do. You take the number of bonds that are coming out of an atom, and we'll count those up in a minute, and multiply that by 2, plus the number of unshared electrons. And I kind of draw unshared electrons as an E minus for electrons, and that should equal 8, or 2 for hydrogen. So hydrogen's unique, it's in the first row. It doesn't actually prefer 8 electrons, but rather 2. So let's go through and actually calculate the octets and verify that this is a valid Lewis structure. So let's take a look at this oxygen over here. So oxygen up there, we're going to count the number of bonds. So we see there's 2 bonds coming out of that oxygen. So that's going to be 2 times 2, because there's 2 bonds times 2. Plus the number of unshared electrons. There are 1, 2, 3, 4 unshared electrons. So 2 plus 2 plus 4 is equal to 8. So oxygen, that obeys the octet rule. Let's take a look at carbon here. The carbon in the center has 1, 2, 3, 4 bonds coming out of it. So that'll be 2 times 4 plus 0 unshared electrons equals 8 as well. And we can do the same thing for the nitrogen right here. So we've got 1, 2, 3 bonds coming out of that nitrogen. So we'll go 2 times 3 plus how many unshared electrons? 1, 2. So that's 2 times 3, which is 6, plus 2, which is 8. So nitrogen also is obeying the octet rule. So we can verify after we draw a Lewis structure that all the atoms have the octet rule obeyed. Except for hydrogen, which likes 2. We can also take a look at one of these hydrogens and confirm that. So like the hydrogen has only 1 bond coming out of it. So that's 2 times 1 plus 0 unshared electrons equals 2. So that's good because hydrogen likes 2. Okay, the second thing we want to look at is formal charge. Okay, formal charge is used when an atom does not obey its valence. So if an atom obeys its valence, then it won't have a formal charge. But if an atom is violating its valence, remember, it's having a different number of bonds than it normally has, then that atom is going to have a formal charge. And that's to show that it's violating something. You have to punish it for violating the valence rule, and the punishment is a charge. Atoms hate having charges. They just want to be neutral. So giving something a charge is actually a punishment. So let's take a look at how to assign formal charge. This is super easy. So let's just draw a different compound here. Okay, we're going to try and assign some formal charges to this compound that I've drawn. So the formal charge formula, Fc, formal charge, is equal to the number of valence electrons, and we'll talk about how to find that in a moment, minus the number of unshared electrons, minus the number of bonds. So let's take a look at hydrogen, for example, here, and we'll calculate the formal charge for this hydrogen. So how many valence electrons does hydrogen have? For that, you look at the periodic table. And remember that to count the number of valence electrons, you just count from left to right. So hydrogen would have 1 valence electron. For carbon, we would count from left to right, 1, 2, 3, 4. Carbon would have 4 valence electrons. So we'll go ahead and do that. So hydrogen has 1 valence electron, so we'll go back here. So hydrogen has, for this hydrogen here, I'll do this in blue. So formal charge equals 1 valence electron minus the number of unshared electrons. Hydrogen doesn't have any unshared electrons, those little lone pair dots that are on the outside of the atom. None of those. Plus minus 1 bond, because the hydrogen's making 1 bond. So that's going to be a formal charge of 1 minus 1, which is 0. So that hydrogen has no formal charge. Let's try this carbon in the middle here. So formal charge of that carbon is equal to the number of valence electrons from the periodic table. Carbon has 4 valence electrons. I just showed how to calculate that. Minus the number of unshared electrons. There are no unshared electrons on this carbon, so that's going to be 0. Minus the number of bonds. There are 4 bonds coming out of that carbon, so minus 4. So the formal charge of that carbon is also 0. Okay, finally, let's do the oxygen up here. Okay, let's do the oxygen. So formal charge equals the number of valence electrons for oxygen. So we look back at the periodic table and we'll count up oxygen. So 1, 2, 3, 4, 5, 6 valence electrons for oxygen. Minus the number of unshared electrons. So we've got 1, 2, 3, 4, 5, 6 unshared electrons for oxygen. So 6 minus 6. Minus the number of bonds. We have 1 bond coming out of oxygen. So minus 1 equals negative 1. So the formal charge for that oxygen is actually negative 1. So what we'll go ahead and do is draw a minus sign near that oxygen and put it in a circle to show that the formal charge is negative 1 for oxygen. You don't typically write the 1, you would just write a minus, and the implication is that that is minus 1. Similarly, if it was plus 1, you would just write a plus sign. It's only when it's like 2 or 3 or 4 that you would then write the number plus 2, plus 3, plus 4. But in this class, typically the formal charges are either going to be plus, minus, or 0. Not going to be any plus 2s or minus 3s or anything like that too much. Okay, so that should help you out with the Lewis structures. Let's do an example problem kind of together here, just to make sure we know how to draw a Lewis structure. So draw a Lewis structure. structure for CH2O. Okay, so if you want to try this, go ahead and pause the video and give this one a try. Otherwise, we're going to solve it right now. So we need to figure out a way to connect everything together to obey the valence, if possible. Okay, so how can we attach these atoms together so that everyone gets their valence obeyed? So carbon likes to make 4 bonds. So it's a good idea. We should probably put the carbon in the middle here. If something has a high valence, that means you probably want it more in a central location because then it can have more branching and can create more bonds. You wouldn't want to put hydrogen in the middle. Hydrogen has a valence of 1, so it's only going to be able to make 1 attachment. So you want to kind of put things with low valences on the outside and things with high valences in the center where there'll be more branching. Okay, so carbon's in the middle. Now we can put some hydrogens. We have 2 hydrogens and an oxygen, and we need to make sure that each hydrogen is making 1 bond and that oxygen is making 2 bonds. So we can think about putting oxygen over here, maybe, and hydrogen here, and you can try different ways of connecting it together, but you'll see that the only way that you can actually fulfill this is if you put the hydrogens connected to carbon. So now the carbon is making 2 bonds, but it wants to make 4, and then we put a double bond to oxygen. This way the oxygen's making 2 bonds, the carbon is making 4 bonds, and each hydrogen is making 1 bond. And you can try as you might, try and attach this any other way. You'll never be able to get it to work unless you do that. Okay, so there's a Lewis structure for CH2O. And we'll have more practice drawing Lewis structures as well. And then, of course, we would need to make sure everyone has 8 electrons. So we need to add some extra lone pairs around oxygen to make sure that it has 8 electrons total. Remember, you add 2 times the number of bonds, so 1, 2, 3, 4, 5, 6, 7, 8, and then everyone else has 8 electrons except for hydrogen, which only wants 2. Now, there's some bad news here in that there are some exceptions to the octet rule that you do need to be aware of. Okay, the exceptions are as follows. Sulfur and phosphorus can have more than 8. It is possible for sulfur and phosphorus to have more than 8 electrons. So for example, one of the most common examples would be sulfuric acid, which has the following structure. See, sulfuric acid, if you look at the sulfur in the middle, we can calculate its electron count using our little formula here. So that's 2 times 6, since there's 6 bonds coming out, plus 0 unshared electrons is equal to 12. So you can see that that is more than 8 electrons. That's an octet rule violation. But it's okay for sulfur and phosphorus. Another example would be boron, beryllium, and aluminum. Those elements can have less than 8 electrons. An example of that that's pretty common is borane. So has the following structure, BH3. Actually worked a lot on this compound in my PhD. And you look at the boron there, and it's got 2 times 3 bonds plus 0 unshared electrons is equal to 6 electrons, which is less than 8. So those are 2 exceptions to the octet rule. Okay, so that's pretty much all we need to say about Lewis structures for now. And I want to now move on to section 1.2, which is bonding. Because bonding is what's fun. Bonding is what makes chemistry interesting. So 1.2, we're going to call this bonding. Bonding is what makes atoms attach to each other. And so before we can talk about bonding, we need to talk about something called atomic orbitals. You maybe remember these from general chemistry. And atomic orbitals have to do with the fact that electrons are wave-like. So let me try and draw a little diagram of what I mean by that. So if we draw a little axes here, an electron is neither a particle more like a wave. So we can kind of represent it like this. It's kind of weird. Electrons are super weird. And what you'll notice is that on this axis, the electron wave crosses the axis several times. And if you remember, these areas where the wave function of an electron is equal to 0 is called a node. So there's a few nodes. That's whenever it crosses the x-axis. And then you can see that it goes from positive to negative to positive to negative. And that's what an electron is. It kind of has a wave. And so these wave-like electrons live inside of orbitals. So for example, we can have something called the 2p orbital. The 2p orbital looks kind of like this. We'll draw a little axis here. X, Y, Z. And the p orbitals look kind of like figure eights. And the p orbitals have phase also, so there's like a plus side and a negative side. I'm just going to shade in the negative side on the bottom there. And this is the z-axis. So because this orbital aligns along the z-axis, we call this the pz orbital. And then we also have some others if they align on different axes. I'll just draw my arrows here. So if we have a p orbital that's aligning along the x-axis, then it's kind of put on its side. And this is the p x-axis. This is the x, so px. And then we'll do one more. We'll do a py. Okay, so now the figure 8 is aligned along the y-axis. This will be our py. Okay, I'm actually going to move these a little bit over, just down here a little bit, and also make them a little bit smaller. There we go. Perfect. Beautiful. Okay, now we also have some, the 2p's are very common in organic chemistry. We also have the 2s orbital. The 2s orbital, there's only one of those. And the 2s orbital looks kind of like a sphere. And actually the 2s orbital has a node on the inside. So it's kind of like a donut with filling inside. And so I can kind of draw it a little bit. It's like there is a node on the inside of the 2s orbital. Now I'm not going to ask you to draw these or anything like that. This is just background information. And then also we have a 1s orbital. The 1s orbital actually has no nodes. And that one just looks like a sphere centered on the axis there. Okay. All right, so those are the common orbitals that we're going to see in organic chemistry, the 1s, the 2s, and the 2p. And so let's just take a look at like, why are we talking about this? What the heck does this have anything to do with organic chemistry? Let's take a look at an element like oxygen. So oxygen is very common in organic compounds. And if you remember how to draw its electron configuration from general chemistry, it's 1s2, 2s2, 2p4. So that's its electron configuration. Now let's try and draw its electron diagram. So the electron diagram is kind of a picture form of this configuration, and where we have this arrow on the left, which is representative of increasing energy. And we can have some orbitals. So we can have the 1s, we can have the 2s, and we can have the 2p. And we'll draw some lines. So there's our 1s orbital. There's our 2s orbital, and we have 3 2p orbitals, the px, the py, and the pz. And now what we need to do, and by the way, because these orbitals are all at the same energy, there's a special word for that. It's called degenerate. Okay. So now what we need to do is fill these orbitals up with electrons, and there are 3 rules that we use to fill these orbitals with electrons, okay? So rule number 1 is called the Aufbau principle. You may remember this from your general chemistry days. The Aufbau principle says that the lowest energy orbital is filled first. Okay. That means we're going to start from the bottom and fill up towards the top. The second rule is, it's Pauli's exclusion principle. And the Pauli exclusion principle says that you must have no more than 2 electrons per orbital. You can't put 3 electrons in one orbital. It has a size capacity of 2. So we'll just say less than or equal to 2 electrons per orbital. And we'll also say they must be opposite spins. So if you have 2 electrons in a single orbital, one must be facing up and the other must be facing down. So we just draw like arrows that look like that. And then the final rule is Hund's rule. And Hund's rule says that we put 1 electron in each degenerate orbital before pairing. Hund's rule is kind of like the bus rule. When you get on a bus and you see there's some empty seats and there's one guy sitting on the bus, are you going to sit next to that guy or are you going to grab your own row? Of course, you're going to get your own row. It's only until all the rows are filled with one person sitting there do people start pairing up and sitting right next to somebody. Electrons like their space. So based on these rules, we can start filling up these electrons into our diagram. So we'll start out with Aufbau's principle, which says we start at the bottom and work our way up. So we'll start at the 1s, and we'll put an electron in the 1s orbital. Now we look at Pauli's exclusion principle. We can't have more than 2 electrons per orbital, and they must be 1 up and 1 down. So we can put a second electron in the 1s orbital, and now that one is full. So now we'll have to move up to the 2s orbital using Aufbau's principle again. Again, we'll put 2 electrons in there. And now that one is full. Now how many electrons, we can look at our electron configuration to see how many electrons we need to put in. And so this should match. We have 2 electrons in the 1s, perfect. We have 2 electrons in the 2s, perfect. And now we need 4 electrons in the 2p. So now we need to use Hund's rule to help us fill the 2p, since now we have our first degenerate orbitals. So obeying Hund's rule, we need to put in 1 here. Now don't put in the second one here, that's violating Hund's rule. We need to put it in its own orbital, just like when you get on the bus, you're not going to sit right next to that guy. So there's the second electron, there's the third electron, and then now all the degenerate orbitals are singly filled, so we put our 4th electron back in the first one, because all the seats on the bus are filled, so now you have to share a row with somebody, and so that's exactly what we did. So that is what the electron orbital diagram looks like for oxygen. And this may or may not be all review. So what does this have anything to do with bonding? Well, it turns out that we're going to talk about something called valence bond theory. Valence bond theory is as follows. So valence bond theory is just this. It's a theory. It's a model. It's not true. It's a lie. It's wrong. It's been proven wrong. But it's very, very convenient for helping us understand how bonding occurs in organic compounds. So valence bond theory is simple. It states the following. Bonds form from constructive interference of electrons in atomic orbitals. Meaning the idea is that electrons are like waves. So if these 2 waves kind of come close to each other, they can interfere either constructively or destructively, meaning the waves can either be aligned with each other, like the positive and the positive align with each other and amplifies that wave and makes it even taller. Similarly, the negative and the negative could combine in phase and make that wave even lower. So constructive interference would tend to hold these waves together. It's a good thing. Similarly, destructive interference, that would be like if a plus and a minus were to interact with each other, that would actually be bad and cause the two atoms to be blown away from each other. So let's take a look at what this looks like in a picture form. So let's say we have a 1s orbital plus a 1s orbital, and they both have the same phase. They're not, I didn't shade them in to show that they're both positive, not one positive, one negative. And when they get close to each other, since they're the same phase, they can overlap. Kind of looks like this. And there's constructive interference between the electrons. And so that's actually going to create a bond. So I'll just draw a bond as like these little blue dots, okay? And this is actually a special type of bond. It's called a sigma bond. And a sigma bond is formed whenever the electron density is on the bond axis. You're probably wondering, what does that mean? Well, we'll see an example where the electron density is not on the bond axis, and then you'll see the difference. Okay, let's try another example. Okay, let's take a 2p orbital. And remember, the 2p orbital has a phase. So unlike the 1s orbital, which is all just a dot, the 2p orbital has a positive side and a negative side. So I'll make the negative side on the left here. I'll shade it in. And let's say that 2p orbital comes close to a 1s orbital. Notice the two white sides are coming close to each other. So when that happens, we're going to get, again, constructive interference. So we'll draw our p orbital, and it's overlapping with our 1s orbital. And we have our shaded side over here. If the shaded side had come close to the white 1s orbital, that would have repelled each other. It would not have been constructive interference. You need the two phases to align with each other. And again here, we're going to make a sigma bond because the electron density is aligned along the bond axis. So you're probably wondering now, how could it be that we could have the electron density not aligned with the bond axis? Well, we'll take a look at this situation. And the chemists, they thought of everything. Imagine we had two 2p orbitals, and they're lined up at a right angle to each other. So we'll shade this side in. This will be our negative side, and the positive side will be on the top. We add these guys together. Well, there's still a possibility for constructive interference, but it's on the top and the bottom now. So I'll just try and get them kind of close to each other. So now there's some overlap that's in phase on the bottom lobes and some overlap that's in phase on the top lobes, but the bond axis itself, there's no electron density there. It's kind of being held together by Velcro on the top and the bottom, but not a direct interaction. So you can see that this is a much, much weaker sort of overlap. It's not as direct overlap of constructive interference of electrons, but rather a more indirect up and down sort of interaction. And this is called a pi bond. And this means that the electron density is above the bond axis or below the bond axis. So pi equals electron density above or below bond axis. Okay, so those are actually the only two types of bonds that we're going to look at in this class. Sigma bonds, where the electron density is on the bond axis, and pi bonds, where the electron density is above or below the bond axis. Okay, well, it would be nice if this picture were enough to explain organic chemistry, but it's not. Let's take a look at an example of why this sort of system doesn't quite account for everything. Let's take a look at methane. So methane is a very common organic compound. It has the formula CH4. Methane. It's an active component of natural gas. It's used as a fuel. It's also a terrible greenhouse gas. So it contributes to global warming. And so let's draw the electron configuration for carbon. Okay, so we'll just draw the little electron diagram. So there's energy. We have our 1s, our 2s, and our 3 2p's. Let me actually just move this over a little bit. So we'll have our 1s, 2s, 2p. We've got our 1s, we've got our 2s, and 3 2p's. Okay. Now, if we fill in this diagram, what we see is it looks like this. So you can take the electron configuration of carbon and you can fill in to draw the diagram, and it would look like this. Similar to oxygen, just it has 2 less electrons. So the 2p orbitals are only singly filled twice. So if you look at this picture, you'll see a problem here, and that is that there are only 2 half-filled orbitals. And so a half-filled orbital can interact with another orbital to create a bond. So looking at this electron configuration, you would think that carbon could only form 2 bonds because there's only 2 opportunities for constructive interference, right? We've got these orbitals are not going to be able to do any constructive interference because they're already full. So they're not going to be able to interact with anything else. These partially filled orbitals, though, they could potentially interact constructively with another atomic orbital. But there's only 2 of them. But that doesn't make any sense because we know that methane has 4 bonds. So our model must be wrong. Bonding must not be constructive interference, right? Like I said, there were some issues with that theory, but we know for a fact that methane exists. So is there a way that we can adjust our model slightly to account for this? And the answer is yes, we can. We can cheat. So we can do something called an excitation. And look at how genius this is. Again, this is not actually happening. This is just a model that humans have created. So we're going to do something called an excitation. Because look what we can do. If we excite one of the electrons in the 2s orbital, we take one of these electrons in the 2s orbital and move it into this empty 2p orbital, look what will happen. 1s, 2s, 2p. I'm just going to move one of the electrons in the 2s upward, exciting it to a higher level. That would totally be a violation of Aufbau's principle, but we're just going to do it just to see what happens. So I just moved that electron from the 2s into the 2p. And now look what happens. We freed up an orbital that was doubly filled and made it singly filled. So now it's available to do some constructive interference. And then also we created a new orbital that's singly filled, creating another opportunity for bonding. So now we went from a diagram that only allowed for the formation of 2 bonds, since there were only 2 partially filled orbitals, to now being able to accommodate 4 bonds. However, there's an issue here, is that we've got different orbitals involved, but we know that methane is totally symmetric, meaning that all the bonding occurs through orbitals that are the same flavor. Otherwise, the structure of methane would be asymmetric. You would have like one bond that's way different than the other 3, but we know that's not true. Methane is totally symmetric. So then we have to do something else, which is called hybridization. So hybridize. And what we're actually going to do is combine the 2s and the 2b orbitals into making one Frankenstein orbital called the sp3. So we're just going to take all of these and Frankenstein them into some freaky orbital called the sp3 orbital. So the 1s orbital is not involved with this. And then now we're going to have something called sp3. And so the 1s orbital, it's like, wow, some crazy stuff is going on above me, but I'm not involved. So the 1s orbital stays the same. And now there are 4 sp3 orbitals that are all the same energy. The 1s orbital still has 2 electrons in it, and then the sp3 orbital has 4 electrons in it. Why do they call this the sp3 orbital? We'll take a look at what it's made of. It's got an s plus a p plus a p plus a p. divided by 4. We're going to take a look at the average here. And what we can see is that this sp3 orbital is made of 1/4 s plus 3/4 p. So the ratio of s to p is 1 to 3. So that's why it's called sp3. Beautiful. So now that we've hybridized our orbital, we can actually draw a picture of what methane looks like. We have carbon in the middle, and then coming out of that carbon, we have 4 sp3 bonding orbitals. So the sp3 orbital looks kind of like a p orbital in that it's like a figure 8, but it's oblong, so it has also like a spherical element to it as well. So it's kind of like a oblong figure 8. So that would be carbon with 4 sp3 orbitals coming out of it. And now there's hydrogens on all the 4 corners. And the hydrogens are contained within 1s orbitals. So they look like this. And you can see there's that beautiful constructive interference between the carbon and the hydrogen atomic orbitals, creating bonds. So this is our beautiful new sp3 orbital. Okay. And another interesting thing to keep in mind is that this angle here between the hydrogens is 109.5 degrees. That's the angle there between. So it's kind of a strange angle there, but 109.5 degrees is the perfect angle where all the hydrogens can be as far away from each other as possible. Now it's kind of annoying to draw this picture every time you want to draw methane, so we can instead draw a quicker perspective view. And the perspective view would look like this. Carbon, hydrogen, hydrogen, and then coming out of the page, we use the wedge to kind of show that it's protruding out of the page into your face. And then the dash would show that it's sort of receding into the page, kind of creating this 3-dimensional shape. So dash means going into page. And wedge means coming out. All right, so this is all well and good. Let's do one more example and then we'll call it a day, because I know this is very, very theory heavy, and I'm not going to ever ask you to draw diagrams like this and stuff. I just want you to understand the theory behind bonding in organic compounds. Let's just take a look at one more example here, and I think this is going to really solidify it for you. Let's take a look at carbon in ethylene. So ethylene looks like this. Okay, and let's take a close look at the bonding of this carbon right here. So let's start again by drawing our atomic orbital for carbon. 1s, 2s, 2p. And our atomic orbital for this carbon looks the same as it did on the previous page. We've got this here. Of course, this would only allow for the formation of 2 bonds. But if you look at this carbon, how many different atoms are attached to it? You've got 3 atoms attached to it. You've got a hydrogen up here, you've got a hydrogen down here, and a carbon over to the right. So we can make 3 bonds, but this diagram only is suggestive of making 2 bonds. Not acceptable. So we'll do an excitation. And we'll do the same thing that we did before and kind of move one of those 2s electrons to a higher level. Okay, but now we're going to do something special, a little bit different than the previous page. When we hybridize now, instead of picking all 4 like we did before, we just are going to pick the minimum that we need to make the 3 different bonds that we need to 3 different atoms. Notice that carbon is, like I said, attached to 3 different atoms. So instead of picking 4, let's just hybridize 3 of them. And let's see what happens when we do that. So hybridize. So we got our 1s. And now our second level is going to be sp2. Since we mixed 1s with 2 p's, we call this sp2. And then we have 1 p left out. Aw, poor p orbital was not included in our hybrid game. But notice that the hybrid orbital, the sp2, is intermediate in energy between the p and the s. So like when you mix these guys together, the new orbital is going to be formed somewhere in between in energy. Okay, so we got our 1s, our 3 sp2 orbitals, and our 1 p orbital. Now we can fill in the electrons. The 1s orbital, it never got to play the game. Our sp2 orbitals, they have 1, 2, 3. And then our p up here with 1 electron, that one was left out of the hybridization game. And so what we can see here is we've got a 1s orbital still. We've got 3 half-filled sp2 orbitals and 1 half-filled p orbital. So now let's see what this looks like when we bond everything together. So we've got our carbon. Draw some hydrogens over here. Another carbon. Draw some hydrogens over here. Okay, now we've got some sp2 orbitals coming out of the carbon. So again, the sp2 orbitals look kind of like the sp3 orbitals, kind of oblong figure 8s. We've got, now the other carbon has the same thing going on. Okay, so those are the 3 sp2 orbitals that are coming out of each carbon. Now we have a p orbital coming out of each carbon. And remember, the p orbital looks just like a perfect figure 8, so that'll be coming out here like this. Okay, and remember the p orbitals, they have phase. By the way, the sp2 orbitals also have phase, but I'm not going to draw that in right now because I don't want to make the picture look too complicated. And so this is what the picture looks like. What we can see here is that we have our sp2 orbitals here. So this is our sp2s. We've got a lot of those sp2s all around. And you can see that the sp2 orbitals are forming sigma bonds. The electron density is along the bond axis. So this one right here, for example, would be a C-C sigma bond. At the same time, look what these p orbitals are making. They're making a C-C pi bond. Ah, interesting. Okay. So that helps us understand the bonding. So if we do a perspective view for this, it would look like this. We've got a carbon, carbon. We've got hydrogen kind of protruding out at us, and another hydrogen sort of receding away. Hydrogen receding away, another hydrogen protruding out. And we have a bond between the 2 carbons. And then we have some p orbitals coming out of each carbon. And those are creating a overlap here. I'm going to draw with like a green kind of circle to show a pi bond being formed as opposed to a sigma bond. Okay. So we'll look at one more example in the beginning of next class. Okay. All right, that's it for today. Thanks for watching.